In this tutorial, I'm going to talk about within-composite differences. It happens very often that we have more than one measure of the same ability, but not all measures of an individual yield the same score. How do we interpret this? Suppose we have two tests, x and y, and they form a composite score. In this case, the individual scored the same on both x and y, 85. The composite score is 82. You'll notice that the composite score, 82, is slightly lower than 85. This is because the composite score is always further from the mean than the average of the test scores that make up the composite. In this case, both scores are the same, and so most clinicians don't think very much about it and just interpret the composite score. However, it often happens that test X and test Y are quite different from each other. The composite score in this case is still the same because the average of X and Y is 85. The question then is how to interpret this score of 82. Should we interpret it the same way, whether that X and Y are the same or different? What's to be done? Why does this even happen? In a previous tutorial, I proposed a taxonomy of influences that is very complex, and most of the time we don't need to worry about the full complexity. But just to review, some influences on test scores are shared, and some are specific. Some influences are transient, short-lived, and some are stable, long-lived. Some are relevant to the construct that we're trying to measure, and some are irrelevant. Most of the time that we study influences on test performance, we have this model in mind. We do not have the full complexity here. We simplify it to this. That is, we have error scores for X and Y. We have a stable but specific ability associated with X and Y. And then we have some sort of common influence, which we assume is the construct that we're measuring. That is, both the error and the specific ability are not relevant to the construct that we're trying to measure. We can simplify further by combining the error term and the specific score into a unique component. That is, we assume that this and this are irrelevant to the construct that we're trying to measure, and therefore we can model it as the sum of error and specific ability. And we can do this for X and Y. So we have this very simple model. That which is common to X and Y, the construct that we're trying to measure, and that which is unique to X and Y, which is irrelevant to the construct that we're trying to measure. Now it is true, we can have more complicated models than this, but most of the time, with structural equation modeling, with confirmatory factor analysis, this is essentially the model that people use. Tests X and Y are added together to form a composite score, and the composite score is thought to reflect the common influence to a greater degree than either X or Y. That is, the whole reason that we add things together into a composite score is that the composite is more valid than either of the subtests. So why would X and Y differ? Well, one obvious reason is that the unique component, that is the specific ability of X and error, and the specific ability of Y and error, are different. That is, differences here cause differences in the test scores. These arrows are loadings, and when they're standardized, they represent correlations. That is, the correlation of the unique component of X with test X is 0.6, and the correlation with the common ability with test X is 0.8. For purposes of illustration, I made the loadings associated with test Y the same, although in practice they don't have to be. The score on test X is 0.6, this loading here, times the unique component of X, here, plus the common score, C, times the loading. And the reason we can add them up this way is that this score and this score are uncorrelated with each other. And we don't have to divide by anything because these are standardized loadings. That is, if we were to square all the influences of X and add them up, they would equal 1. That is, 0.6 squared plus 0.8 squared is 0.36 plus 0.64. Add them together, it equals 1. This score here is a z-score, this is a z-score, and this is a z-score because we're assuming that these all have a mean of 0 and a standard deviation of 1. However, z-scores are difficult for clinicians to think about because we tend to use t-scores, scaled scores, and standard scores. I'm going to use standard scores or index scores, a mean of 100 and a standard deviation of 15. So suppose the common ability equals 100. And the two unique components are 70 and 130. That is, the unique component of X is 2 standard deviations below the mean, and the unique component of Y is 130, 2 standard deviations above the mean. It doesn't happen very often that you get this combination. About 2 in 1,000 cases you'll get this particular combination, and then 2 in 1,000 cases you'll get the reverse score. This is 130 and that's 70. That is, 1 in 200 cases you'll get a discrepancy this large. So if the unique component of x is 70 and the common score is 100, what is the score for test x? Well, we're going to use this equation. X minus 100 divided by 15 is test x minus the mean of 100 divided by the standard deviation of 15. This yields a z-score. Likewise, this here will yield a z-score, and this here will yield a z-score. And we multiply the two z-scores by the loadings. So let's plug in the numbers. This 70 went right here, and this 100 went right here. So 70 minus 100 is going to be negative 30, and 100 minus 100 is going to be 0. Negative 30 divided by 15 is negative 2, and 0 divided by 15 is 0. Now this 0 is going to multiply this and become 0. This negative 2 times 0.6 is going to become negative 1.2. We're going to multiply 15 by negative 1.2 and get negative 18. And then we're going to add 100 to both sides to solve for x. And x is going to be 82. So this 82 is going to go here. And we can do the same process for test y, but I'm going to spare you the arithmetic and simply say that if we apply the same kind of equation, we're going to get 118. So this difference, 82 and 118, doesn't happen very often for two tests that are as correlated as they are. By the way, the correlation can be found by simply multiplying the two loadings on the common factor. 0.8 times 0.8 is 0.64, so that's the correlation between x and y. So two tests that have a correlation of 0.64 are not this discrepant very often. About 1 in 200 cases have a discrepancy this large. The composite score can be calculated with this equation here. So we're going to do 0.8 times 0.8 for the correlation between x and y, like so. And then if we work out the arithmetic, we get a composite score of 100. Now, how is it that this score and this score happen to be exactly the same? Well, because these two things essentially canceled each other out. They're both 2 standard deviations from the population mean. One is 2 standard deviations below the mean. The other is 2 standard deviations above the mean, and therefore they cancel each other out. Now, the reason that they could do this is that these loadings are equal. We'll see later that when they're unequal, this doesn't work out exactly this way. Here we have a case in which the common score is perfectly estimated by the composite score because the two unique components, even though they're substantially different from each other, they cancel each other out. In a future tutorial, I'm going to talk about the difference between these unique components and how they affect our interpretation of the composite score. But I'm going to move on to another reason that x and y might differ. And I've already alluded to it. It's differences in loadings on the common factor. So in the example I've been using, these two loadings are exactly the same, but they don't have to be exactly the same. They can be quite different. So, for example, this loading here now is 0.9 and this loading here is 0.5. Because they're standardized loadings, these loadings have to change as well. That is, this squared plus this squared have to equal 1. When the loadings are substantially different, the unique components can also cause the test scores to be different, but I'm going to hold them the same for purposes of illustration. So I'm just going to put them right at the mean. They're each 100. Now, if the common score is also 100, these two scores are going to be the same. If we use this equation here to solve for x, we're going to put in 100 here, we're going to put 100 in here, and then we're going to multiply by these loadings, and then solve for x. I'll do this very quickly. Substituting in 100s, they become zeros, multiply by 0 becomes 0, multiply by 15, still 0, add 100, and test x is 100. We could do the same thing for test y, it would also be 100, and so what we have is unequal loadings causing the same score here. Now, the only reason that happened was that this common score is right at the mean. However, if this common score differs substantially from the mean, something very different will happen. If it's more extreme, that is, far from the mean in either direction, we'll see that these scores will differ substantially even though the unique components here are the same. Suppose that the common score is 130, 2 standard deviations above the mean. The unique components are the same, so they're not going to cause any differences. But you'll see that because this is far from the mean, these scores will differ from each other. So if we apply the same math, we'll get this situation here, where they differ by about 12 points. If this score differs even further from the mean, like let's say 145, the differences between x and y will become even greater. The composite score in this situation would be 125. So we see that this and this are not that far from each other, but it does differ somewhat. We could fix this by weighting test x more strongly than test y if we knew the loadings, but if we don't know and we just weight them equally, we're going to get this situation where we're not going to estimate the common score very well. This works exactly the same way if the common score is below the mean. So if the common score is 60, substantially below the mean, we'll see that test X now is 64 and test Y is now 80. So there's quite a big difference here, about 16 points. The composite score in this case will be 67. You can see that it's 7 points off. There's a third reason that X and Y can differ, and it has to do with moderators. What's a moderator? A moderator is a variable that changes the strength of a relationship between two other variables. In the models that we've considered so far, this correlation coefficient, this standardized loading, is constant no matter what. A moderator is something that changes how big this correlation is. A simple way to think about the moderator is that it's it depends variable. So when you say, what's the relationship between this and that, and you say, it depends, what does it depend on? It depends on the moderator. The formula for y is additive. That is, we take some coefficient, we multiply it by the common factor, and then some other coefficient, and we multiply it by the unique component of y. With moderators, we have multiplicative relationships. So I have some sort of moderator, and it's a categorical moderator in this case. That is, it's either a 0 or a 1. It's either absent or present. And its effect is going to be not on test X and not on the common factor, but on the loading between X and the common factor. We could have a continuous moderator, but I've decided to make it simple for this example. The strength of the moderation in this case happens to be negative 0.8. I'll explain what that means. The formula for X is a bit different than the formula for test Y. So here we have X equals some coefficient here, but now it's a dynamic coefficient. It depends on M, times C. So here we have C times some sort of coefficient. Here we have C times a dynamic coefficient, a coefficient that changes depending on the value of M. Then we have the coefficient for the unique component of X here. So what does this mean? Well, this coefficient, this loading, is dynamic. It equals 0.9 minus 0.8 times M. And M can be either a 0 or a 1. So if the moderator equals 0, then the loading is 0.9 minus 0.8 times 0. Multiplying by 0 gives 0, so it's just going to yield 0.9. However, if the moderator is present, then we're going to get 0.9 minus 0.8 times 1, which is going to be negative 0.8, and 0.9, which gives us 0.0. That is, the relationship between the common factor and X is dramatically reduced if the moderator variable is present. If it's absent, then the test performs as it's intended to. If this moderator thing is present, then the relationship between the common factor and the test is essentially severed. That is, they're barely correlated at all. Now, I've been speaking abstractly. Let's give some examples to flesh this out. Suppose that test X is a measure of visual spatial ability, like a paper folding task, where we have to imagine that a paper is being folded, and then we cut holes in it and do all sorts of things to it, and then we unfold it, and then we ask the person to imagine what the folds look like and where the holes would be in the paper after it's been folded, punched, and then unfolded. There are two categories of ways of solving this task. One, we could use visual spatial ability by imagining a paper being folded in the mind's eye, imagining the holes being punched in the mind's eye, and then imagining the paper being unfolded and see how it would look. And then we would compare our imaginary representation to an array of choices being offered by the multiple choice test. Another way is to use an analytic process. That is, we can imagine, okay, there are two folds, and then there's one hole punch, and therefore we're going to have at least two holes after it's been unfolded. That's not using visual spatial ability, it's using logical deductive abilities to eliminate answer choices. So if I use one kind of strategy, the test is measuring visual spatial ability. If I use another kind of strategy, using a logical deductive reasoning strategy, then my test is not measuring, for me, visual spatial ability, because I'm not imagining what it looks like. I'm not visually simulating this movement. Note that if I use some alternate strategy that doesn't involve visual spatial ability, does not mean that I'm going to get the answer right, and it doesn't mean that I'm going to get it wrong. That is, the test performance is going to depend on how good my other abilities are, but it doesn't depend on the thing that I'm trying to measure. Now, it's possible that the moderator not only affects the coefficient between the common factor and test X, but also affects test X directly. That is, in this example, I have an effect on this coefficient here, but I also have a strong negative effect on test X directly. So, for example, I once tested a woman with a vocabulary test, and she misunderstood the directions. She thought that we were doing a mental association test. So if I asked her, what's the definition of dinner, for example, she would talk about family dinners and her father and all sorts of interesting things from a clinical perspective, but she never got around to actually defining what dinner was. If I were to continue giving the test in that way, knowing that she misunderstood the directions, she's going to get every question wrong and she's going to get a very low score. But it doesn't reflect her vocabulary ability, it reflects her understanding of the directions. So, the moderator variable in this case is, does the person understand the directions? If yes, score 0. If no, score 1. If the person doesn't understand the directions, we are severely misestimating the person's vocabulary ability. If the person doesn't understand the directions of the test, they're going to perform poorly. It is possible for the moderator not only to have a relationship with this coefficient, but also with this coefficient as well. And so we can imagine all sorts of possibilities. We don't have to stop there. It could also have an effect on these coefficients and on this test, like so. We don't have to stop there. We can imagine more than one moderator, but I've only shown one here. So we can have many, many, many moderators having all sorts of different effects. Now, most of the time, you as an astute clinician will be observing what's going on, and you'll be able to see the kinds of moderators that I've been talking about. Sometimes they're hard to see, but most of the time, when you see that, hey, it doesn't appear this person's approaching the task in the right way, the clinician simply disregards the test score and tries again with a different test, with different directions to make sure the person understands, and to make sure that the test is appropriate for the person. So you would interpret the meaning of the test very, very differently if the person culturally is very different from the standardization sample. So essentially what moderators do is they alter the validity of the test, in which case we're not going to be interpreting the tests in the same way. So here are 3 reasons that X and Y would differ. This is not a comprehensive list, so you can imagine others, but these are pretty important ones to keep in mind. In the next tutorial, I'm going to focus on this first reason for X and Y differing. The unique component of X is different from the unique component of Y, and it causes these 2 scores to be very different from each other. And I'm going to talk about what impact does that have on our interpretation of the composite score.